So last up, before we have discussion, we have Gautam,
Maybe.
maybe.
Still not being updated. I'm sharing screen, yes, but that's not up on the projector.
That's weird.
Yeah,
So Gautam or Dance is
don't tempt me. All right. I realize I am the last person keeping you from food, which is always dangerous. But let me tell you folks a little bit about what we've been doing in SCIMMA. And in particular, I'm not going to give you a whole picture of things. Curtis is going to be talking to you on Friday, and we'll tell you some of the other stuff that we've been working on. But let me tell you about the stuff that we've been doing on the AI front. You've heard SCIMMA multiple times this week already. SCIMMA is a group that has been building a pub subsystem to connect different surveys together, things like LDK, AMON, the GCN itself, IceCube, and we have been building the connections, for example, as you've heard from Shreya, to Rubin's TOO system. We handle IGWIN alerts. We handled all of the O4 alerts, both internally and externally from LIGO. We didn't have a single second of unscheduled downtime during and the nice thing about all of this is you can go sign up for the service on your own. You don't need approval from anybody, including me. We've made this so simple that a postdoc can go do this. So, August folks, if you need to stream alerts, happy to help. Just go sign up. It's all cloud-based. It's all scalable. It's easy enough to get to run. There's Python clients. And people always ask, where does SCIMMA fit in an ecosystem diagram? And we can always cast our ecosystem diagrams to put yourself in the center, which is always a great trick for funding agencies. But the key is actually that the thing that SCIMMA is building isn't a single box. It's the arrows that connect the boxes. Now, we talked a little bit about rapid response, and one of the things we've been focusing on is sort of the ground-based equivalent of a cross that has some other functionalities. This is a thing that we've called Heroic, and you'll hear about this from Curtis on Friday. And it really is about coordinating observatories. It works really, really well, and he'll be able to show you a full demo of things. But the thing that I wanted to take away from and start with today is that AI is everywhere. I mean, if you aren't worried about your jobs, I don't know what to tell you. You should be. And it kind of needs to be everywhere because we are trying to do a lot of science at Rubin's scale. And it really is necessary if you want to try to do multi-survey, multimodal data. And none of our traditional machine learning techniques do that sort of thing. This became very evident to me when I was considering the same sort of science case that you heard about from Jacob Norden and I Smaller in the broker session, type 1A cosmology. I'm a recovering type 1A cosmologist. For my sins, I now run the Dark Energy Science Collaboration as their spokesperson and spent many years designing a pipeline to do type 1A cosmology. And lo and behold, every one of those blue diamonds in my pipeline to get us to cosmology is some AI model. And this is a terrible, terrible idea because you have n different training sets, n different pieces of code that now all have to be maintained for 10 years of Rubin. And now you have to also sneak in Roman and Euclid on top of this. Oh my God. So it struck me that a lot of the things that we were building, other people needed too. You heard some of these things today from the brokers, host association, photometric redshifts, whatever else we are needing, other people probably need too. And a lot of these tools really benefit from the long tail of data that's buried in archives. So we've started putting together services where we think we can connect things that the community needs in a simple way. Host association and just generally host property in inference is one of these. And you'll hear more about an updated model that will be deployed called Frankenblast. But I can show you the original version called Blast in a second. So Blast has processed every single transient that's on WiseRep to date. And this is live. So we have a service called blast.scimma.org. So every one of the supernovae that's been reported and has finished processing, you can sort of go through and select. Let's just pick one down here. I don't know. I'm just going to pick that one for random. Ooh, excitement. And so BLAST is going to go off and retrieve downloads, postage stamps for a whole bunch of different surveys. Those are loading off in the corner. And you can see that it's grabbed a whole bunch of these postage stamps. It's done local and global aperture photometry at the location of the supernovae. And it uses a prospective SPI model to actually take UV through IR data and give you a full SED. And it does this all online in about 800 seconds for this particular object, but it varies between 400 and 800 depending on how slow it is to retrieve the postage stamps, basically. All of this is online in the cloud. You don't have to do this. And I can assure you that grad students used to do this for their theses. So it's just become easier. Now, one way to interpret what I've done here with a service like BLAST and making it a web service with my colleagues, David Jones, Peter McGill, and Andrew Manning at NCSA, is that we moved from doing upstream tasks that you've heard about during this conference, things like cosmic ray reduction or real bogus, to doing a very downstream analysis task. And we moved from using some kind of like purely empirical model for the data, like features on a light curve and trying to separate them out or segmentation, to doing physical inference, properties of that host galaxy, things like specific star formation. And the model might be wrong. I'm sure Anya will tell you tomorrow that the BLAST model is wrong and you should use Frankenblast. But who cares? It's useful. Every model is wrong at some level. We've also moved from like really nice heterogeneous data to like just using data that's in archives online. You don't have to have tabular columns. You can have missing passbands, and it just works. And what you'll see from Charlotte Ward tomorrow as well, and she's somewhere in this room, is that you can actually extend this further. So Charlotte is part of the team within the Dark Energy Science Collaboration, working with me to extend this to Euclid processing as well. So we took Rubin DP1 data and Euclid Q1 data, and Charlotte and Peter Melchior and Erfan Nurbakhsh, who's a fabulous postdoc at Princeton, have done a lot of the processing to actually get you to scene model photometry for these galaxies, as well as full SEDs from the UV through optical and IR. I'm not going to tell you more about that. You should wait for Charlotte's talk tomorrow. It'll be fabulous. And so we can, of course, take the code that she's written and just put it in BLAST and do this, right? For every single Rubin plus Roman plus Euclid supernova there is. And that's Rubin and Euclid and Roman are great because they are big surveys. They produce nice data sets for the most part. They have annual data releases. But then there's things like WISE-REP. And WISE-REP is a much bigger challenge and requires a larger team to work with. But thankfully, I also happen to be deputy director of one of the NSF Simons AI centers and have a cool team of people who wanted to work with fun things. So to give you a picture of what WISE-REP looks like in pie diagram form, one of the most common classes of supernovae that has been reported to WISE-REP is man. You can't train a machine learning model on this. There's like 70,000 real spectra, period, okay? So we wanted to learn how we could actually build a model for spectroscopic classification, and we've been doing that. We developed a method to not just simulate light curves, but also simulate spectral time series of supernovae of different classes. We trained a model that's transformer based on all of this, and then we made it a service, just like BLAST. And we did this all in a month with an undergrad named Jesus Carbello during his MIT JTOM. And it works. You can upload a whole batch of supernovae, or you can choose our transformer model or the Dash model. The transformer model is a little bit newer. I'm not going to show that off quite yet because this is not truly an AI talk, but I'll take the existing Dash model since many of you are familiar. My favorite supernova, because it was the first one I ever observed, even though this is dating me, is SN 2002 ER. I went and took a last spectrum of this. So I'm very attached to this particular supernovae. And you can see that in real time, once I put that name in the Dash says, oh, this is a 1A. Cool. But more fun than that, it takes the latent space projection of that supernovae and says, well, where are the nearest neighbors for this thing, or for any of the supernovae that we have in WISE-REP that are publicly available. And so you can pick your favorite supernovae that's publicly available and click them, and it'll put you a little X on there, and you can adjust the number of nearest neighbors near there. You can zoom in and see, well, what does that look like? And it gives you a cosine similarity distance in a high dimensional latent space projected down to two-dimensional t-SNE, and says, oh, look at these other things that are nearby. You scroll down, you can actually look at their spectra. And this is useful because although they really do look similar, that's cool. And these are all different objects. You can see that from the legend. That's cool because you can do anomaly detection. You can look for the objects on WISE-Rep that are mislabeled. Promise you'll find lots and lots of mislabeled things. And again, this took 1 month to put together by an undergrad. So it's a lot of very powerful infrastructure. In fact, one of SCIMMA's new products is going to be the infrastructure to build services like this for your own AI models. And if that's of interest to you, also come talk with us. The transformer model is even more fun. We've been training it, like I said, on the simulated supernova sample, and you have like a flat 10% improvement over Dash. And that's kind of bonkers to me. You're training on completely fake data. You're doing some domain adaptation with fine tuning to the real data, and you get an improvement in performance across the board. So modern AI methods, even if they're trained on simulated data that's not all that realistic, can do some pretty amazing things, which is a food for thought for folks who are thinking about how to adapt to Rubin. You need some other services to feed these AI models, particularly the things like you heard about from Guille, where you need a stamp classifier. And as we've heard, the Rubin postage stamps are kind of crummy. And so we built an alternative. We wanted to have a high throughput bulk download service for stamps. And so we built a cutout service. I have run this on one of those objects already. You give it an array and a deck in some size. It goes off, spins up in the cloud, cutouts from any service, any survey that has postage stamps. Right now it works for DECCAM and PANSDARS. But as Rubin gives us postage stamps, or as we go through MAST, we can do that as well, and give you any cutouts that exist for that service or for that location on the sky. You can specify your size. Turns out cutouts are pretty easy. So if you need a training set for these big large language models or your favorite AI tool, please use this tool. We're also working with Nevin and his team at Link Frameworks to make LSDB a service for brokers. I think it's nuts to have brokers each individually do cross-matching. Each of these catalogs are terabytes. So let's just build one cross-match service that bulk loads and cross-matches Rubin alerts and makes the cross-matches themselves available. And then finally, I did promise multimodal data, and I showed you images and I showed you spectra. So I should also show you stuff with light curves. We're training a model called Selden. This is a foundation model for supernovae. Again, I trained it on simulated elastic data, and then I threw this completely on real data. And instead of showing you classification, I'm showing you forecasting. It's predicting the future of the light curve as it sees observations. So the more and more points it sees, those points become shaded, and it predicts the future. And it can do this in a completely class-independent way. It has no knowledge of the redshift or the labels for the supernova. It does pretty well. It's also connected to the actual underlying physics for many of the models. There's a paper that was accepted at AAAI in Singapore earlier in January for that. It's a fun foundation model. It's same model you can use for anomaly detection and similarity search. So hopefully you're seeing where this is going. I'm going to put all of these things together into one big model and host it online for all of our web services, because why not? It already works with real Rubin alerts. We've tested that out. And the real fun thing with something like Selden is that you can run the entire Elastic data set through it, and it takes about 240 seconds to do the entire 4 million things. And I couldn't resist with Matthew's Lord of the Rings meme, putting my own Lord of the Rings meme in there, which is basically that, yeah, with a few GPUs, even A100s, you can totally handle the Rubin alert stream, and now it's not a big deal. So how this all fits in the future is you have multimodal data from things like Rubin and Euclid. You combine them, you throw them at a foundation model. You can do things like physical inference, but also anomaly detection, also recommendation for active learning, and trigger your follow-up. And it's all one happy ecosystem. So if you want some takeaways, I would say that large language models aren't new. And they only really became useful when people found ChatGPT online and could use it. And they became powerful when ChatGPT had the MCP protocol to connect to other services. And that's basically what we're doing in SCIMMA now. We build arrows, and now we're building arrows to enable AI services. So I was also asked to answer some questions, and so I will do so in as spicy a manner as possible. What have we learned from the existing alert streams and Rubin alerts? I think getting data to the community is the best way to actually optimize the telescope software stack and get science out, and also secure funding. So the lack of Rubin alerts recently is a critical failure in my mind. Are we ready for alerts from Roman and beyond? No. Have you seen a Roman schema? Do you have any Roman brokers really properly lined up? I mean, we're literally chatting about them and being like, yeah, we'll do this at this conference. That doesn't mean we won't manage when Roman launches. I think people will pull all-nighters and get science done. And you should give them the credit for that. But let's not pretend that we're actually ready for Roman alerts. How do we optimize transient discovery with multi-wavelength and multi-messenger streams? Trove from Griffin and others seems to be doing a really good job to coordinate people. I think heroic that you'll hear about from Curtis will be coordinating observatories. And I think to coordinate the actual data, that's AI models. And then how do you actually use machine learning? People, nobody's going to fund machine learning anymore. This is not the 20th century. If you're doing machine learning as a grad student, run away and do something properly. And we call it AI. And the last question we were asked is, what's the physics of stellar explosions and variability that can be revealed with all of these multi-wavelength observations? And for that, please fund my Roman cycle 1 proposal.